Hello dear students, I am back with my second lecture on General Organic Chemistry. In last lecture of Reaction Mechanism Part 1, we were discussing factors that influence organic reactions which are also termed as electronic effects. As I already told you that this General Organic Chemistry part is the most important part of chemistry. If these basic concepts are clear to you, then it makes organic chemistry a very easy subject. So be attentive, just listen carefully and get rid of fear of organic chemistry. In last lecture, we discussed about first factor, that is inductive effect. Before going to second factor, I must tell you that inductive effect has many applications which we will discuss in many other chapters. It can explain relative stability of carbocations, relative stability of carbon ions, relative acid strength of various acids, relative basic strengths of various bases. Now we come to second factor, that is Mesomeric effect or resonance effect. It is basically a stabilization phenomena where polarity in a molecule is produced due to interaction between pi bonds or pi bonds and lone pair of electrons. Just like inductive effect, here also the effect is transmitted along a chain. In conjugated systems where double bond and single bond are linked alternatively, pi electrons are delocalized as a result of mesomeric effect, giving rise to various resonating structures. Resonating structures, which are also termed as canonical forms, are just hypothetical and does not represent the actual molecule. The actual structure of these compounds is combination of all of these, which is known as a resonance hybrid. The resonance structure must have same position of nuclei. That is, arrangement of atoms in canonical structure remains same. It does not changes. And secondly, it has the same number of unpaired electron, but they differ in position of pi electron. The pi electron position changes during resonance. Here we are giving the example of resonating structures of acetate ion, which is formed by removal of proton from carboxylic acid. Here in this acetate ion, the negative charge or pair of electron, it is shifted over here and pi electrons are shifted over here. As a result, the single bond is converted into double bond. This double bond here is converted into single bond. A negative charge is developed over here. These are the resonating structures of benzene, which also differ in arrangement of pi electron, and here also delocalization of pi electron takes place. These two structures are known as Kekule structures, and these three structures, remaining three, they are known as Dewar structures. And the actual structure, which is known as resonance hybrid, is combination of all of these, and it is represented in this way. Now here the circle in between, this represent delocalized pi electron cloud. The possible resonating structures must have valid Lewis structure which obey octet rule. Now the energy of actual molecule is much less than the energy of various resonating structures, and the difference of energy between the most stable resonating structure and the actual structure, which is known as resonance hybrid, this difference of energy is termed as resonance stabilization energy, or simply the resonance energy, which results in stabilization of the molecule. The next point is, more the number of contributing structures, more will be the value of resonance energy, and as a result of high value of resonance energy, molecule will be relatively more stable. Now, when a compound has more than one non-identical or different type of resonating structures, then the stability of these resonating structures will be different. Then following points are considered. Among resonance structure, the one which has more number of covalent bonds, or in other case, when all the atoms with the octet of electron are there, or in other case, less separation of opposite charge, or in other case, more dispersal of negative charge is there, then that type of structure will be relatively more stable, and more stable form will contribute more to the resonance hybrid. Now, mesomeric effect is also of two types, plus M effect and minus M effect. Now, first we come with the plus M effect. Now, in this type of effect, transfer of electron is away from the atom or substituent group that is attached to conjugated system. And when this type of electronic displacement takes place, then certain position of the molecule becomes negatively charged, or we can say which has high electron density. Now, the atom or group of atom which shows plus M effect are OH, OR group, OCOR, NH2, NHR2, NR2, NHCOR, etc. This type of plus M effect is observed in case of aniline, which is shown over here. In aniline, NH2 group is attached to benzene ring, where nitrogen has a lone pair of electron. Now, this lone pair of electron is in conjugation with this multiple bond, double bond. So, mesomeric effect will be there. Lone pair of electron is shifted over here. Pi electron are shifted over here. This results in formation of double bond between carbon and nitrogen. This nitrogen acquires positive charge, and here as pi electron are shifted, this has negative charge on it. Now, here again negative charge is in conjugation multiple bond. Further resonance will take place, and these are the resonating structures of aniline. Now, here in aniline, negative charge is developed on these two positions, which are termed as ortho position, which we will discuss later in the chapter of aromatic compound. And this particular position which has negative charge, this is termed as para position. So, negative charge is developed on ortho and para position in aniline due to this type of plus M effect. Now, second type of effect is minus M effect. This is just opposite to that of plus M effect. Now, here transfer of electron is towards the atom or substituent group which is attached to conjugated system. Now, when this type of electronic displacement takes place, then certain position of molecule has positive charge on it, or we can say here electron density is decreased, that is they have low electron densities. Now, the group which shows minus M effect are COOH, CHO group, carbonyl group, C double bond O, CN, NO2, and so on. This is the example of compound showing minus M effect, that is in nitrobenzene. This type of mesomeric effect or resonance is there. Now, here nitro group is attached to benzene ring. Now, these double bonds are in conjugation with each other. So, mesomeric effect is observed, and as a result of this type of mesomeric effect, positive charge is developed on these two positions which are termed as ortho position, and here also positive charge is developed, and this position is meta position. So, in case of nitrobenzene molecule, positive charge is developed on ortho position as well as at para position due to minus M effect. Now, this is important slide. We have to remember when resonance phenomena will be there. So just remember, whenever multiple bond are in conjugation with each other, or either positive charge or negative charge or lone pair of electron is in conjugation with multiple bond, then mesomeric effect or resonance phenomena will be there. These are the 4 different examples. In first case, double bond is in conjugation with each other, double bond, single bond, then double bond. So here pi conjugation occurs. In next case, this double bond is in conjugation with lone pair of electron, and that's why here also mesomeric phenomena will be there, and here p-pi conjugation occurs. This is allyl carbocation where positive charge is in conjugation with multiple bond, so here also resonance phenomena will be there. In case of allyl carbanion over here negative charge is in conjugation with multiple bond, so here also mesomeric effect is observed. The application of resonance phenomena is most important in case of explaining the properties of especially aromatic compound. Most of the properties of aromatic compound can be explained by this mesomeric effect phenomena. Now we come to next factor, that is electromeric effect. This is the third one which influence organic reactions. Now this electromeric effect is a temporary effect, and it is observed in the compound which have at least one multiple bond in it. Multiple bond means either a double bond or triple bond should be present over here. And when such type of molecule is attacked by a reagent, then under the influence of reagent, pi electrons are transferred to one of the participating atoms. Now this effect is observed at the demand of attacking reagent, which means that as soon as the attacking reagent is removed, pi electron comes to its original position. It means it is a temporary effect, and it is represented by this type of arrow. Now again, electromeric effect is also of 2 types, plus E effect and minus E effect. First we come to plus E effect. In this type of effect, the pi electron of multiple bond are transferred to that atom to which the reagent gets attached. Now this is the example. This is an alkene molecule. It is attacked by electrophile, say H plus. Now when electrophile H plus approaches alkene, pi electrons are shifted to this particular carbon, and now this attacking reagent H plus attacks on this carbon where pi electrons are shifted, and that's why this effect is termed as plus E effect. Other effect is minus E effect. Now here in this type of effect, pi electron of the multiple bond are transferred to the atom to which the attacking reagent does not get attached. For example, again this is say alkene molecule. This is attacked by reagent Cn minus. Now here cyanide ion, which is a nucleophile, it attacks on this particular carbon where pi electrons are not shifted, and that's why this type of effect is termed as minus E effect.